Always, sometimes, never. Here we have let x and y be vectors of size n, and we want them to be non-zero vectors, and let the angle between them be equal to theta. Then the cosine of theta is the dot product of x with y divided by the length of x times the length of y. Is this always, sometimes, or never true? And again, since we're giving a picture to help us think through this and a hint, I suspect it's always true. But as I did for the last problem, one of the things I wanted to do first was to remind ourselves of the picture and ahead of time look at what we know. We know by the law of cosines that the length of x squared plus the length of y squared minus 2 times the length of x, length of y, times the cosine of theta is the length of y minus x squared. How do I know that? It's the law of cosines, and I actually looked it up on the web just to make sure that I wasn't mistaken with one of my signs here. And I wasn't. So we know this must be the case. And so for my proof, I'm just going to say, let's let x and y be non-zero vectors as described here, and they're arbitrary other than that. And the angle between them has to be theta. Why must they be non-zero vectors? Because if they were the zero vector, the length would be 0, and we would be dividing by 0, which wouldn't make any sense. So in this particular case, what we're going to do is look at the law of cosines. We'll start here. We know that would mean that the norm, or the length of y minus x squared, which is c squared, must be equal to the length of x squared plus the length of y squared minus 2 times the length of x times the length of y times the cosine of theta. And that is just the law of cosines. Now, this is equivalent to, well, the length of x minus y squared, you might recall, is just the inner product of y minus x with itself. And this is actually a lemma, but it's very similar to the problem that we looked at last time. If we expand this, we'll get y transpose y minus 2 times x transpose y plus x transpose x is equal to, now the length of x squared is just x transpose x. The length of y squared is just y transpose y. And then we'll have minus 2 times the length of x times the length of y times the cosine of theta. And again, I'm going to be a little sloppy here, but I'm going to call this a lemma, and I'm going to ask you to verify it for yourself. In other words, make sure that this minus in here doesn't mess up our expansion any, and it expands naturally like this. It's not hard to prove, but I really should have proven the lemma. Now, if you believe me, then now we can do some arithmetic and simplify. This expression is equivalent to Let's see how we can simplify here. We have a y transpose y as a term on the left-hand side and also on the right-hand side of our equation. We have an x transpose x on the left-hand side and also on the right-hand side of our equation. And we're left with minus 2 times x transpose y is equal to minus 2 times the length of x times the length of y times the cosine of theta. And this is the case just because of arithmetic. When I wanted to simplify the equation, I could subtract like quantities from both sides. I want to solve for the cosine of theta. So what I'll do is divide both sides by this quantity. And the result will be minus 2 times x transpose y divided by minus 2 times the length of x times the length of y, again by arithmetic. And clearly we can simplify, and this gives us that the cosine of theta must be equal to x transpose y divided by the length of x times the length of y, which is exactly what we wanted to prove. So yes, it is always true.